Welcome to part 4 of our video series on VASA. We'll be exploring the example pictured here, which features 2D slices or sections of a building. It also includes a Python script. After that, we'll check out a few nodes for working with solids and meshes. So let's begin. So here we're in Dynamo, and we'll go File Open. And these are the examples that come with VASA. In the previous videos, we've gone through examples 1 through 9. So now we'll load up example 10. So example 10 shows how to work with slices of voxel models and convert those slices into images. So here we have a building, and you can see one two-dimensional slice in each dimension. So if we go to the graph, we see that it starts off as the other examples. We take in the geometry from STL files, we voxelize it. Here's the voxel model being displayed, and if I just disconnect that color, just to use the default color, we can see the building more clearly. We're using a very coarse resolution in this example. We're using 50 centimeter voxels, which is much coarser than usual, but this is just to speed up the calculations. So let me go and connect that translucent color again so we can see the slices. Okay, so what's happening here is we have these sliders here that control the index of each of these slices. So for example, if I increase the X index, you can see that slice move to the right. If I increase the Y index, you'll see the green slice move back. And if we increase the Z index, we'll see the blue slice move up. The vertical direction is a bit slower because there's more voxels. Let me undo all that and go back to what we had originally. And so we'll go through how we're creating these slices. And to do that, actually, let's just focus on the slice in the slice for the X dimension. So we'll go and hide the green voxel model and the blue one. So now we're just seeing this one slice. And this is being created using the slice iterator feature of VASA. So if we go to the VASA menu on the left and we go into iterators, there's two types of iterators: slice iterators and voxel iterators. Slice iterators let you go through each slice of a voxel model in each direction. So that's what we're using here. Voxel iterators let you traverse each individual voxel, although that tends to be a little bit slower. So if you have a choice, it's best to use the slice iterators. So for this node here, we're creating a slice iterator using this by voxel model and X index node, which means you give it an X index, then it gives you a slice in the Y and Z directions for that index. So here the index is 4. Just to show you what the index means, it actually means like it's the fourth slice from the origin. So if I create a point, then by default this point will be right at the origin, and this slice is basically 4 voxels to the right of that point. To make that a bit more clear, let's set that slice index to 0. And so now that slice will move so it's right beside the origin. It's actually, if I just click on that point again, it's actually just to the right of the origin. Like it's the origin is on the side of this slice of voxels. if we set the index to -1, it'll be just on the left-hand side, just on the negative side of the origin. So let's change that back to 4, which was what it was originally. And just to be clear, it's actually, these slice indices are actually relative to the origin of the axes of the voxel model. But by default, the origin of the axes is just 0, 0, 0. So that's the origin here. Okay, so let's delete that and take a closer look at how it's producing the slice. So we're creating a slice iterator. We're giving it the voxel model. We're giving it the index, and that creates a slice iterator object. And then we've got various functions that we can use with the slice iterator. For example, we've got advance, which will create a new slice iterator that's offset from this one by a certain amount. We have isValid, which will just check whether that slice is actually within the voxel model or if it's outside the voxel model, in which case it'll be not valid. Here we're using the slice voxels node and the slice data node. So what the slice voxels does is it takes the slice iterator and gives you a new voxel model, which is just 1 voxel thick. And so here we're just creating that voxel model, that 2-dimensional voxel model, and displaying it in red. So what's actually being displayed here is a voxel model, which is just 1 slice of the original voxel model. And here we're accessing the data of the slice. And if we just click here and take a look at what that looks like, it's just basically a list of lists of zeros and ones. So kind of like a 2-dimensional array of zeros and ones. So that first list is a row, and it's actually the top row because we have this start at upper row parameter, and we're giving it the value true. That means it starts at the top. And so what this is saying is, it's from the top left, we have 3 empty voxels, 1 filled voxel, and we have a whole bunch of empty voxels, and then a bunch of filled voxels, and it keeps going after that. But so 3 empty, 1 filled, bunch of empty, and a bunch of filled. And now if we look at the voxel model, and we see at the top row, so it starts off with 3 empty voxels. We can't quite see all 3, but there's 3 empty ones. Then there's that 1 filled voxel right there. Then there's a whole bunch of empty ones and a whole bunch of filled ones. So that data that we're seeing here in zeros and ones is exactly the data that you're also seeing here. And then when we have the voxel information in the form of these lists, we can then go and we can go and process it in different ways. But here what we're doing is we're converting that array into a set of colors, a matching lists of colors, and we're just using black and red. And then we're taking these colors and creating an image. So then we're getting this image, which is exactly what you see here in 3D. And of course, if we change the slice index, it will update the image as well. I'll just undo that. Okay, so that's what's happening there. And if I turn this on, we're doing the same exact thing in all 3 dimensions. So we just have this, basically this copy and pasted set of nodes here. So here we have the slice iterator by voxel model and Y index, and at the bottom the by voxel model and Z index. So the same thing, but being done in each dimension. Okay, so those are how to work with slices and images. There's just one more thing in this example that's worth checking out, and that's the Python script down here. So this Python script, move things around a bit. The Python script is it's just taking in that voxel model, the original voxel model of the building, and what this script does is it outputs a list of voxel count. So this list here is the number of filled voxels in each slice of the building in the vertical direction. So the bottom, the bottommost layer, the bottom slice, has 22 filled voxels, then 22, then just over 8,000 for the next ones, etc. And the point of this is just to demonstrate how Python scripts work, so that you can do your own Python scripts, maybe more elaborate ones. So let's check that out. Generally speaking, with the Python script, you can do anything you can do in Dynamo with a graph, you can do in a Python script, and you can do even more with the Python script, because you can import different libraries and write code with loops. So let's see what's happening here. Okay, we see the first 4 lines are just standard lines that are put there by default. Then we have this line that accesses the slice iterator from VASA. And actually, this will only work if we're in Python 3. So actually, look, if you go down to the bottom, in this version of Dynamo, we have a choice between Python 2 and Python 3. Make sure you use Python 3 if you have the choice. So now we're importing the slice iterator. It turns out that even if we don't have that line, like even if I comment that out, the script will still work all the way down to line 25. You'll see there's an error here at line 25. But these first few lines will all work. So you can get a voxel model as your input. You can get the finest level of detail. This is a VASA node, but it knows which one it is. You get the extents, you calculate the dimensions. So all of that works just fine. But down here on line 25, where we're creating the slice iterator, here we have to access this by voxel model and z index function right here, this node here. And to access that, we're going to need to import it. So we have this line here. I'll uncomment it now. From VASA.iterators, import slice iterator. So VASA is the topmost level, and then under VASA you have core iterators, operations, pathfinding, utils. So from VASA.iterators, and then the next level is when we import. So import slice iterator, and you can do that to access all the functions in VASA. And so here that gets us this slice iterator node. And just to point this out, if there's a different way of doing this. If we want, we could comment this, and we could go import VASA, just import VASA at the top, and then over here we would have to type VASA dot iterators dot slice iterator, etc. So if I save that, that should also work. Yeah, that's working at the right there. So that's another way to do it. If you just want to import VASA by itself, then you have longer function names later on. Or if we do it this way, where we're importing individual nodes or individual types, then we have shorter function names down below. So let me save that. By the way, when you click the save, it applies the changes you made, so it'll run the graph, but it won't actually save the file. So I'm not saving the file here, but I am pressing the save button to apply the changes to the code. So let's take a look now at what this code is doing. So it creates an empty array of filled voxel counts, which is what it's going to output at the bottom. But in the middle here, it loops over all the slices in the vertical direction. So while the slice iterator is valid, so it starts the slice iterator off at the lowest Z index. This gets you the lowest Z index from the extents of the model. So it starts off at the lowest slice, and then while it's valid, like while the slice is still within the model, it does all these steps. First it gets the slice data, which you saw as the list of lists of zeros and ones. It initializes the next voxel count to 0. Then it loops over all of the y indices, all the voxels in the y direction, and gets that row of voxels. So it gets the row of the slice data at the index iy, and then for each row it loops over all of the columns or all of the x indices, so all of the individual voxels. Then here, row data ix is the individual voxel value. It's either 0 or 1. If it's 1, it adds 1 to the current voxel count. So that's what it's doing in there. And then here, there's a very important line of code on line 53 where it advances the slice iterator. It's very important. It advances it by 1. It moves it up 1 level. And if you don't have that line, of course, you'll just have written an infinite loop, which will never finish. So you have to have, so that line's important, and it just keeps advancing it until eventually it'll advance it above the top of the model. At that point, the slice iterator will become invalid, then we'll exit the loop and exit the function. Okay, that's what that's doing. So I mean, it turns out that we can actually do the same thing in quite a bit less code. So in fact, if we just let's create a new line here and write filled voxel counts dot append. So we're going to append a new voxel count. All we have to do is now go slice iter, the slice iterator, dot slice voxels this time, which gets a new voxel model. Then we can just use the count filled function to count all the filled voxels in that slice. And then close bracket. And I think if I haven't made a mistake, I can delete all of this code all the way down to the line that advances the slice, which we have to keep. And now if I run that, I think that's giving me the same thing. So that's all we actually needed. But the reason why we do all this instead, so I'm going to actually delete that change. The reason why we did all this instead was to demonstrate how you would go through all the voxels if you needed to. So you might have a more complex operation, which requires you to go through all the voxel data. So then here is how you traverse it. You might also want to output the voxel data to a file, and this is a good way to do that. So you could write a Python script that opens up a new file and it goes through all the slices and writes the data to the file, and then so that would be a way to get data from VASA, into a file and then you can bring it into another program and analyze it there. Okay, so I think we'll leave it there for this example. Let's go file open. There's just a few more functions I'd like to share with you, so I won't bother saving. Let's go back and open up the first example, the overview example that we saw in the first video. Okay, so this is the example that demonstrated all the features. But I'm going to go and hide I'm actually going to go and hide everything for now. So go to select all these blue nodes and hide all geometry preview. And let's just start by looking at this geometry here, preview. So this was just three pieces of three geometry objects: a cuboid for the ground, a cylinder for the trunk of the tree, and a sphere for the foliage of the tree. And let's see, here, what we're doing here in this example is we're bringing it into this voxel model by geometry node. I just want to show you a few other things we could do with it. So if we go to the VASA menu and go into Utils, we can go into triangles as 9 numbers from geometry. So now we can take that list, those 3 objects, and convert them into 3 lists of triangles, of triangle data. And now from there, we can let's go and right click and type flatten and just use the flatten operation to take these 3 lists and convert them into one big list. And now if we wanted, we could use the voxel model by triangles node and give it a coarse voxel width and voxelize it that way instead of by geometry. But actually what we'll do here instead is let's go and use the toMesh node in Utils again. So that takes the triangles and creates a Dynamo mesh. Let's hide the original geometry so that we can see the Dynamo mesh. And now it turns out there's Dynamo meshes, and there's also meshes from the Mesh Toolkit package. So here I've got the Mesh Toolkit package installed. You don't need to install the Mesh Toolkit to use VASA, but you can if you want. So their Mesh Toolkit includes this by vertices and indices node. And if we want to convert a Dynamo mesh to a Mesh Toolkit mesh, here's what we would do. So first of all, the Dynamo mesh is up here in geometry meshes mesh. We can use vertex positions to get the vertices. And that's a set of points. I'm going to hide that. And then connect those points to the vertices. And then we can also access the face indices. But we can't quite connect these face indices to the indices parameter here. And that's why VASA includes, if you go down to VASA utils, it includes this vertex indices by triangle type. Then we can go, I think, from index groups. It says note useful for converting a Dynamo mesh into a Mesh Toolkit mesh. So now we take these index groups, convert them into a list of indices, and now we can convert our Dynamo mesh into a Mesh Toolkit mesh. Let me turn off the Dynamo mesh so that we can see the mesh in the Mesh Toolkit format. Okay, I'm running out of space here, so let me just highlight all those nodes and move it down over here. Okay, and once you have a Mesh Toolkit mesh, you can use the functions that come with the toolkit. So, by the way, we actually didn't need to do this in this case because we had the original geometry, so you can convert the geometry into a Mesh Toolkit mesh. But sometimes you end up with a Dynamo mesh, but you don't have the original geometry. So in that case, these functions from VASA are useful for converting it to a Mesh Toolkit mesh. Once you have a Mesh Toolkit mesh, you could use any of these functions here. So for example, let's use the there's one that reduces the number of triangles. So let's do that. Let's reduce it to 200 triangles. And turn off the original mesh. Okay, so now we've got the same thing, but with the reduced number of triangles. And if we want, now we can use in Mesh Toolkit, we could use triangles as 9 numbers. And now we have it as this list, and this is exactly the kind of list that we can voxelize if we want. So we can create a by triangles voxel by triangles and connect that up. And if we gave it a coarse voxel width, it would voxelize these triangles. But just to show you one other option, if we go to VASA, utils, another thing we can do with these triangles as a list of numbers is we can export it to an STL file. So if we connect it up to export to STL, then we have to give it a file path. So if we were to right click, type file path, we could browse, we could type in a new file name and connect that up, and it would export these triangles to an STL file. Okay, so those are a few of the mesh-related features that you get with VASA, which may be helpful before you voxelize your data. Okay, and now there's just one last thing we should cover. So I'm actually going to turn off, I'm going to actually hide all this over here. And let's show the building voxels. And let's actually give it a translucent color. Advanced, reduce the alpha. Okay. And let's also turn on the view voxels. Okay, so last thing we're going to show is just different ways to view voxel models. So let me just rearrange a few things. So I'm going to move this display voxels node over here. I'm actually going to create a code block and type in voxel model semicolon and just connect this up. So we're just focusing on what we need. So we can use the display voxels node, which is the fastest way to view a voxel model, and probably the way I would recommend if you don't need to do anything besides view them. When you use display voxels, you get this object called a voxel tessellation object, and you can't do anything with it. It's only there to view the voxels, and what it does is actually lumps the voxels into these cuboid shapes. And so if I were to go inside, this whole region should be filled, but if I go inside, you can't see much there. But there's a couple other options. So if we go to VASA core voxel model, there's the display voxels. We've also got 2 cuboids and 2 solid. So we'll bring those up. So let's see what those do. So 2 cuboids is a little bit slower than display voxels, so it'll take a little while to compute. But once it's done, it'll give us basically the same thing, but as a list of Dynamo cuboids. So hopefully, yeah, I think that's finished. So if I click this list, in this case, we actually get a list of cuboids. And so we have an object that we have objects that we can process using Dynamo, other Dynamo features. We could bring these into we could bring these into Revit or Format, for example, and view it there. So there's a little more we can do with it. We can also, if we want to color it, we can just bring up the standard by geometry color node, and so we can feed that in and connect that color. I'll hide these cuboids. So now we're seeing exactly the same thing we would with the display voxels node. And if we go inside, we end up inside one of these cuboids. By the way, you might think it's creating a separate cuboid for each voxel. It's not doing that. So if we actually look at the number of cuboids, there's 5,000, a bit over 5,000. If we look at how many filled voxels there are, we can go to count filled, and we'll find out that there are 380,000 filled voxels that you see here in green. So what it's doing is it's lumping those voxels together into these larger cuboids so that it can display it more efficiently. It would take forever if we tried to actually create a separate cuboid for all of these 380,000 voxels. Okay, so that's 2 cuboids. Now the last one is 2 solids, so I'll connect that up. And this one is the slowest by far. In fact, if you have a very large model, it may never finish. So if you do want to use the 2 solid node with a large model, you might consider using the technique we saw in the previous example, where you iterate through a model slice by slice, and you can maybe convert each slice into a solid. But what this does, instead of giving you a whole bunch of cuboids, it gives you one object, one piece of Dynamo geometry that you can then process using Dynamo's features. You can do intersections with other objects, for example, and this solid just represents the outside of the voxel model. So when that finishes, we'll see that one object appear. Just to save some time here, I think I'll connect up the okay, there it is finally. Okay, so there's the solid object. I'm going to connect that to this color node and hide this one. So now we see it in color. So this is one solid representing the boundary of this voxel model. And now if we go inside, it'll look quite different from before. You can actually see it's hollow inside. So I'm going to try to navigate. So we can try to go through the inside of it, and you'll see that point there. That's the point that was, remember, these are the voxels that are visible from a point. So that there's a point in a room, and that's the one we were using to generate this model. And so you can see that, well, basically the entire room is visible from that point. You can also see through the 3 windows there. You can see through this door into another part of the building. And if we turn around, you can see out this door here and out the building all the way to that tree in the courtyard area. Okay, so that's the 2 solid node, which is there when you need it. Okay, so I think we'll leave it there for this video. If you have any questions or any feedback on VASA, please comment on the video. Also, let us know if there's any other aspects of VASA you'd like us to cover in a future video. Again, please check out the description of the video, which has links to other resources, and we'll try to add new links as new resources become available. All right, thanks for watching.